These are the objectives for this course. Recall from your heat transfer course, a heat exchanger transfers heat from one fluid to another fluid. In order to transfer heat, the two fluids must have a temperature difference, and there must be a path for heat to flow from the hotter to the cooler fluid. Heat exchangers are characterized by the direction of flow the two liquids have relative to each other. In a parallel flow heat exchanger, the tube side fluid and the shell side fluid both flow in the same direction. As they flow through the heat exchanger, the fluids transfer heat, and the temperatures of the two fluids approach each other. Note that the cold fluid temperature is always less than the hot fluid temperature. The major disadvantage of the parallel flow heat exchanger is that the hot fluid outlet is always hotter than the cold fluid outlet. In a counterflow heat exchanger, the two fluids flow in opposite directions. The fluids enter the heat exchanger at opposite ends. Counterflow heat exchangers generally produce the highest average temperature difference of the three types. This high average temperature difference translates into higher heat transfer rates for a given size and construction. In a cross-flow heat exchanger, one fluid flows perpendicular to the second fluid. That is, one fluid flows through the tubes and the second fluid flows across the tubes at a 90-degree angle. Cross-flow heat exchangers are often found in applications where one of the fluid changes phase, a two-phase heat exchanger. An example is a steam condenser in which the steam enters the condenser shell side and the cool water flowing in the tubes absorbs the heat from the steam, condensing it into water. The shell and tube type heat exchanger consists of a cylindrical container called a shell holding a set of tubes. One of the fluids flows inside the tubes while the other fluid flows outside the tubes. The fluid flowing inside the tubes is called the tube side fluid, and the fluid flowing on the outside of the tubes is called the shell side fluid. The support plates also act as baffles to direct the flow of fluid in the shell back and forth across the tubes. Tube bundles have many tubes, sometimes hundreds, depending on the size of the heat exchanger. The tubes are supported on the ends by a tube sheet. In systems where the two fluids are at different pressures, the higher pressure fluid is inside the tubes, and the lower pressure fluid is on the shell side. The smaller diameter tubes can withstand higher pressures than the larger diameter shell of the heat exchanger for a much lower cost. One method to improve the performance of a heat exchanger is to have the two fluids pass each other several times within the same heat exchanger. When a heat exchanger's fluid pass each other more than once, it is called a multi-pass heat exchanger. If the fluids pass each other only once, it is called a single-pass heat exchanger. Multiple passes are achieved by inserting baffles on the shell side of the heat exchanger. The baffles direct the shell side fluid back and forth across the tubes to achieve the multi-pass effect. From the outside, the heat exchanger looks like a simple counterflow heat exchanger, but on the inside is a multi-pass counter and crossflow. You should become familiar with the parts of a multi-pass heat exchanger. Another common method to increase the number of passes is to reverse the flow through the heat exchanger by placing one or more sets of U-bends in the tubes so that the tube side flow enters and exits on the same end of the heat exchanger. These types of tubes are known as U-tubes. The U-tubes allow the fluid to flow through one way and then back the length of the heat exchanger. This is a shell side of a shell and tube heat exchanger. You can see the baffles along the flow path from the inlet to the outlet. The flow is entering the shell side from the inlet on the bottom of the shell and exiting through the outlet on the top. You can see the change in direction through the length of the shell as the liquid flows around the baffles, causing the liquid to go across the tubes multiple times. A plate type heat exchanger uses hollow plates instead of tubes to separate the hot and cold fluids. The hot and cold fluids alternate between each of the plates. Baffles direct the flow of fluid between the plates. Because each plate has a large surface area, the plates provide each of the fluids with a large heat transfer area. Therefore, a plate-type heat exchanger, as compared to a similarly sized shell and tube heat exchanger, is capable of transferring more heat. This is due to the larger area the plates provide over tubes. Due to the high heat transfer efficiency of the plates, plate-type heat exchangers are usually very small when compared to a tube and shell-type heat exchanger with the same heat transfer capacity. The plates in a plate heat exchanger can be thinner than the tubes in a shell and tube heat exchanger. The combination of the thinner plates and the larger surface area allow a smaller size plate heat exchanger. Plate type heat exchangers are not widely used due to the difficulty of reliably sealing the large gaskets between the plates. Because of this problem, plate type heat exchangers are normally used only in small, low pressure applications such as oil coolers for engines. This shows us the flow path for the cooling fluid in blue and the hot fluid in red. The cooling fluid flows through every other plate on either side of a hot plate. The hot liquid flows through the other plates not used by the blue. The liquids never intermingle. Shell and tube heat exchangers still have two significant advantages over plate heat exchangers. They are simple to construct, and the tubes can withstand higher pressure than the flat, hollow plates can. The advantages of plate heat exchangers are small size and the ease of maintenance. A plate-type heat exchanger is capable of transferring more heat when compared to a similarly sized shell and tube heat exchanger. Several different factors can affect the heat transfer rate in a heat exchanger. Recall from heat transfer the equation for heat transfer across a boundary. Heat transfer rate, Q dot, is equal to the heat transfer coefficient, U, times the area, A, times the differential temperature, delta T. If U and A remain the same and the difference in temperature between the fluids increase, what will happen to the heat transfer rate? The heat transfer rate will increase. Another factor is metal thickness, which affects the heat transfer coefficient, U. The thinner the metal, the easier it is to transfer heat across it. If the heat transfer coefficient goes up and area and delta T remain the same, what will happen to the heat transfer rate? It will increase. Another factor for the heat transfer coefficient is if there is material insulating the tubes or plates, making it harder to transfer the heat. This can occur with fouling, buildup of corrosion, crud, or sludge around the plates or tubes, or if air pockets, an air blanket, surrounds the tubes or plates. This reduces the heat transfer coefficient because it is harder to transfer through this buildup than the metal alone. If U decreases and area and delta T remain the same, the heat transfer rate will decrease. Another factor is the type of heat exchanger. We said that for the size, a plate type heat exchanger has more surface area for the heat transfer. If the area increases and U and delta T remain the same, then the heat transfer rate will increase. Heat exchangers are used in any process where heat needs to be moved from one location to another. These include cooling oil and water in combustion engines, facility equipment cooling water systems, air conditioning evaporators and condensers, generating and condensing steam for steam systems, preheating liquids for process equipment, refrigeration, and many more.